car starts from rest and travels for 5.0 seconds with a uniform acceleration of 1.5 meters per second squared.
So T1 is 5.0 seconds. And acceleration 1 is 1.5 meters per second squared.
The driver then applies the brakes, causing a uniform acceleration of -2 meters per second squared.
A2 is -2.
A2?
Or no.
Sorry. Oh, that's fine. I'll write it. One of the things that I try to make sure you guys do is you always use the words rather than just giving me the symbols, because in the long run, it's much better for your brain. You will remember the stuff much better if you tell me what they represent. So acceleration 2, I'm sorry, Highwind was what?
Negative 2.0 meters per second.
2.0?
If the brakes are applied for 3 seconds, how fast is the car going at the end of the braking period, and how far has it gone from its start?
So time 2 is 3.0 seconds. I'm not really sure what's there. Would you use the
We're not solving the problem. We're understanding the problem first. We're missing stuff. I don't know what we're trying to find, right? So far we just have a bunch of known variables, but I don't know what we're trying to find.
So we're trying to find the distance from the final initial.
So what do I write? Right? So Highwind, understand, your job is to translate all the words into symbols, because it's symbols we use and letters we use to represent stuff. Right? So that's the main job. And this is one of the harder pieces, is to figure out what all of this represents. So what are we trying to find here? Leo, help us out. What's going to be equal to question mark? We're missing that at the moment.
Trying to find the first part of the question, trying to find velocity. It says how fast the car is going at the end of the period.
So I'm going to write velocity is equal to question mark. Is that what you're saying?
Yeah, but
Yes, but? But what? What do you think? You're not happy with that?
no, it doesn't make sense because I'm not sure what you're supposed to do with the second. So I'm not sure how you're supposed to calculate.
Okay, all right, that's fine. So we've got some more velocity, but we're not really sure. Fine. Nicole, please.
Well, can we say that velocity initial is 0?
Okay. An important thing to realize is at the very beginning it says it starts from rest. So you should identify that our velocity initial is equal to 0. This is an important piece of information. Okay? We have another question mark. Who can tell me what else is equal to question mark? And we're going to there's some stuff we need to fix. That's fine. Bless you as well. What else is equal to question mark? Dang it. Joe.
The distance traveled.
So what am I going to write?
X equals question mark and a change in X.
Ah, so that's an important difference. X represents a position, right? They haven't asked us for a position, they've asked us for how far we've gone, which is going to be the magnitude of the displacement, which is delta X. Good. We still have a bunch of stuff to fix here. There's things to fix on the board. Who's got something for me? Emily.
Limit the time growth number to be like in change over time.
Neither of these are a specific time, but rather a time duration. So it's a change in time. So this is delta t2 and delta t1, the change in time for each one. Now, let's understand what's going on, because I agree, Leo, we got to figure out what this really is. Okay, so let's understand what's going on. We have, for a while, and a spot where we put our foot on the gas and we accelerate. We know right here the velocity initial is equal to 0. True. We know an acceleration for this. Now, we've identified 1s and 2s. So this we're going to call part 1. So for part 1, we have a certain change in time. It's equal to 5.0 seconds. That's too small. We've got all the numbers written up there. We've got a certain change in time for part 1. We've also got an acceleration that exists for part 1. Right? Then we put our foot on the brake. So this is where we have our foot on the gas. Then for part 2, we have our foot on the brake. And we have a change in time for part 2, and we have an acceleration for part 2. Good. Let's start with this initial velocity. What subscript is missing from this initial velocity?
The 1.
This is the initial velocity for part 1. V1 initial. So that is the initial velocity for part 1. Okay. We're missing subscripts on both of our things that are equal to question marks. Who can give me, both things we're trying to find, who can give me a subscript on either one of those? Hi.
So V is supposed to be down.
Well, what does it specifically say in the problem? Chris, what's this velocity? You would have read it to us. You read to us, that's why we're coming back to you. But I was hoping you would read it to me again, because what specific velocity was it looking for? It says,
how fast is it going at the end of the braking period?
how fast is it going at the end of the braking period? Hyland, what is that then?
Oh, so it's in
V2.
V2.
The velocity for the second part final is what we're looking for. That's right here. The velocity for the second part final, V2 final. That's what we're trying to find. Leo, does that make sense? Yeah. Good. Delta x, they were looking for the magnitude of the displacement for what? We don't have a subscript on that. Sound good?
Sorry, what was that?
We're trying to figure out this piece, but we don't have a subscript on it. So, Chris, what does it ask for then? How far has it gone from the start? So what subscript do we put on that?
Initial or one?
Right, so that's the question.
I'm
Maria wants to help you out.
total.
Total. How far has it gone from the very beginning? So this is the total. So the question is, what is the displacement or the magnitude of the displacement total from the beginning to the end? Class, have we started solving the problem yet? No. Do we have a much better understanding of the problem now? Yes, okay? So remember, you need to understand the problem first. Now, we're going to talk about how we're going to solve this. General approach, who has a general approach on how to solve this? Nicole.
Well, what we can do is we can use one of the equations for uniformly, accelerated motion or whatever.
UAM, uniformly accelerated motion. What makes you think that we can use the UAM equations? Hennessy. For part 1, the acceleration is the same. What leads you to believe this?
Because it says for the first 5 seconds, it says a uniform acceleration of 1.5.
it says right here, the acceleration for part 1 is 1.5 meters per second squared. So that means we can use the uniformly accelerated motion equations because the acceleration equals a number, okay? That's true both for parts 1 and for part 2. You can see that. So you can see we need to use the UAM equations in order to solve this. Great. So let's start out by just looking at part 1. Part 1. Let's list all the stuff we know for part 1, just to make sure we have them all. Dawes, what do we know for part 1?
We know the acceleration for part 1.
Is?
1.5 meters per second squared.
Good. What else do we know for part 1?
We know the change in time
For part 1 is
is 5 seconds.
5.0 seconds. We know also
The initial velocity
is the velocity for part 1 initial is equal to 0. Okay, class, please remind me, there are how many UAM variables? Try again. Class, there are how many UAM variables?
5.
How many UAM equations?
4.
If you know how many of the variables,
3.
you can figure out the other.
2.
This leaves you with 1.
Happy physics student.
Happy physics student. So, you can see we're going to use UAM. We have, for part 1 class, how many variables that we know?
3.
So we can find the other 2. So we just have to figure out how we're going to do that and what exactly we need to find. Help us out, Andrew.
Well, let me take a look. So we know velocity initial and acceleration and time. So we could find the final velocity with velocity final equals velocity initial plus the acceleration times time.
Change in time, delta t. He's missing a subscript on all 4 variables. What subscript is that, Olivia?
I don't know.
It's okay, we'll come back. Missing a subscript. Terrible. Mark.
Number 1.
The number 1, because this all refers to part 1. So this is velocity for part 1 final, velocity for part 1 initial, so on and so forth. So we have velocity 1 final, velocity 1 initial, acceleration 1, and change in time 1. Okay. So we now know velocity 1 final equals 0 plus the acceleration for part 1, which is 1.5, multiplied by the change in time for part 1, which is 5, which is going to give us velocity for part 1 final is equal to 7.5 meters per second. Now, I don't know why we did this. We're looking for velocity 2 final. We found velocity 1 final. Adam.
Velocity 1 final would equal velocity initial for the second part.
Notice, we just figured out the velocity for part 1 final. But that is also equal to the velocity for part 2 initial, because the end of part 1 is the beginning of part 2. So we didn't just find velocity 1 final, we found the velocity for part 2 final. Because if we look at part 2, we only knew 2 things to begin with. We knew the acceleration for part 2, which was negative 2.0 meters per second squared, and we knew the change in time for part 2, which was equal to 3.0 seconds. But that's only 2 of the 3 UAM variables we need. We just figured out the velocity for part 2 final, initial. Velocity for part 2 initial is equal to 7.5 meters per second. Okay, what next? Haley?
Do we have to do part 2?
I don't know, what are we trying to find now?
Well, I don't know if this is relevant, but I would find the delta x for the first part.
Okay, go ahead. Let's see if that's relevant.
So delta x1 equals velocity initial 1 times delta t1 plus half the acceleration 1 times delta t squared.
Change the time for part 1 squared, right?
Oh yeah.
Okay. So we've got the displacement for part 1, velocity 1 initial, so on and so forth. Sure, we can figure out we have 0 multiplied by the change in time for part 1, which was 5, plus 1/2 times the acceleration for part 1, which is 1.5, times the change in time for part 1, 5 quantity squared. So the displacement for part 1 is equal to. Yep, yep.
18.75 meters.
18.75 meters. So we just figured out the displacement for part 1 from there to there. Okay. What else would you like to do, Helen?
We can find the final velocity for part 2.
How are we going to do that?
We can use the same equation, so velocity
Velocity for part 2 final, good.
velocity for 2 final is equal to velocity 2 initial plus acceleration 2 multiplied by change in time 2.
Yep, as you said, we're using the same equation, only instead of for part 1, we're using it for part 2. And we have, as you said, all that information, 7.5 plus the acceleration for part 2, which is -2, times the change in time for part 2, which is 3. The velocity for part 2 final is equal to 1.5 meters per second. And that is an answer. One of the things we're trying to find. Okay, so we have figured out half of it. Velocity for part 2 final. You turn it off for me,
Yeah.
please. Okay, velocity for part 2 final. What else can we do, Bob?
You can find the displacement, like x, changing x to.
The delta x for part 2, the displacement for part 2, okay.
And you
How?
You do like velocity 2 initial, and then times the delta t2, and plus 1/2 acceleration 2, and you multiply that by delta t2 squared.
Great. What are all the numbers here, please, Kathy?
7.5 meters
Velocity 2 initial, delta t for part 2,
per seconds.
plus 1/2 times the acceleration for part 2,
-2,
times the or the change in time for part 2.
3 seconds.
It's 3 squared. So the displacement for part 2 is equal to yeah,
15.5.
13.5 meters. So we're close. Jack, what are we doing next? Jack, what are we trying to find? Remind me, what are we trying to find? We've already translated what's in the book, right? So going back to the book right now and reading is probably not the best move. I would come back to the board and look at what were equal to the question marks. We already figured out velocity 2 final, right? So what's the other thing? One more, bless you. Total, okay? We just figured out the displacement for part 2, and we illustrated what we were trying to find right here, the displacement in the x direction total. Add them. Add what together? The displacement for part 1 plus the displacement for part 2 is equal to the displacement total, right? And you can see that visually from the little picture we drew. The displacement for part 1 was, bless you, 18.75. I think I was supposed to bless that, I'm not sure. 13.5. The displacement total, please. Nicole? 32.25 what? Meters. Therefore, the displacement total with the correct number of sig figs is equal to, Tyler?
It would be 32.3 meters.
Tyler, going back, 5.0 has how many sig figs?
2.
2. How many sig figs on 32?
It would be 32.
32. All right, so let's take a moment, look at what we did. Notice givens, question marks, little picture to help understand how everything works together. Listing part 1, part 2, the stuff that we know. Listing an equation with appropriate subscripts, using the equation, listing another equation with the appropriate subscripts, and so on and so forth. Do you see how clear what we've done here is? Yes? Yes, Ellen?
On the homework, like, would we have to draw?
You don't have to draw it. It's helpful for understanding what's going on, but no, it is not absolutely necessary that you draw. I have a question. One of the UAM equations is that the displacement is equal to 1/2 times the velocity final plus the velocity initial multiplied by the change in time. If we were solving for the displacement total, why didn't we simply do that the displacement total was equal to, well, the final velocity is v2 final, the velocity initial is v1 initial, times the change in time. So we have 1/2 times the velocity 2 final, well, this would be the change in time total. So the velocity 2 final we figured out was 1.5, the velocity 1 initial was 0, the time total would be 3 plus 5. Why doesn't that give us the correct answer, Emily?
Because like we wouldn't know that like the velocity of the final for the second problem is the same as the velocity of the final. It's like the variables.
But this is, I mean, if they were talking about displacement total, this would be the velocity for the second part final, right? This would be velocity for the first part initial, because for the total thing, this would be the final, this would be the initial. We'd have to change the time total.
They didn't show how you do that.
Ah, but we could do that. Mark, it would still be wrong. If you look at the numbers, we're still getting the wrong thing. Mark.
The time at which like the velocity was like whatever amount was different than what it was for what part 1 was.
But the total time would be 3 plus 5, right?
Yeah, but
you guys are missing the main piece here. It's a very important piece to understand why this is wrong. Maria.
Those subscripts are different. One's part 2 and one's
You can do them where you have different subscripts in the long run. There are times when you can't. It's a very simple thing, Cash.
You have to use the acceleration.
We do not have to use the acceleration. This is the one UAM equation that does not have acceleration in it. Adam.
It's because the acceleration is uniform from the beginning to the end.
You can only use the UAM equations when the acceleration is uniform. That's what uniformly accelerated motion means. The acceleration is uniform for part 1, right? It's written right there, 1.5 meters per second squared. The acceleration is uniform for part 2, negative 2.0 meters per second squared. But you can't use the UAM equations and have it encompass parts where the acceleration changes. Do you see how the acceleration changes from part 1 to part 2? Do you see how it's no longer uniform then? Okay. So the UAM equations only work for durations where the acceleration is constant. That only works for the first 5 seconds. And then we have a whole different set of UAM equations for the second 3 seconds. Because it's a different event, therefore it's going to have a different uniform acceleration. Before we move on to numbers, Dawes, question?
Would we be able to use that equation to find the change in x for part 1?
Let me back up. By that equation you mean this one?
Yes.
Yes. So actually, once we got to having the velocity final for both of these, all three of the other equations we could have used, we would get the same answer, because we now have 4 of the variables. So it doesn't matter which one you would use at that point. Yes, delta x equals 1/2 times velocity final plus velocity initial times delta t, part 1. You could also do velocity final squared equals velocity initial squared plus 2 times the acceleration times the displacement in the x direction for part 1. They'll all give you the same answer.